So in this video, what we're going to do is we're going to start looking at representing power functions as power series. And so one of the great things that we can do with a power series is that we can use it in order to represent functions and a lot of different kinds of functions. And the reason why that's so handy is because polynomials are really easy to do things like differentiate, take the derivatives of, and to actually integrate. All of those kind of things. It's kind of easy. It's a lot easier to work with them than it is to work with other kinds of functions. In addition to that, sometimes there are functions that we can't do calculus with. And so working with its power series representation can oftentimes make it a lot easier or make it possible so that we can go out and find integrals, so we can go out and find derivatives, so that we can actually do functional analysis, what's called functional analysis. So with that, we're going to look at, first, let's remember that a geometric series, okay, is the sum n equals 1 up to infinity of r to the n, where r is our common ratio, and that is going to end up equaling 1 over 1 minus r. Now, this is basically one of those things that this is an explicit equation for a representation, right? Okay, so for a power series, if we kind of think about it. And what we can do here is we can actually substitute in x to the n, right? And make it actually into a power series. So the sum x to the n equals 1 up to infinity is then just going to equal 1 over 1 minus x. All right, basically what we've done is we've substituted in x for r. All right, now we know for a geometric series, for this series to be convergent, x is going to have to, or r will have to be less than 1. So along the same token, okay, if x is less than 1, then the power series ends up being convergent. All right, so that's something that we're going to just have to remember. That basically what we're looking at here is we're looking at a representation of a geometric series, all right, but instead of having a common ratio, what we've got here is we've got a variable x. And if x is less than 1, that's our radius of convergence, then we end up having a convergent power series. Or excuse me, yeah, convergent power series. So now what I want to do right now is I want to take a look at what happens, okay, and why it is that we actually have those two things being equal to one another. So this red line is 1 over 1 minus x. And then I'm going to look at from x equals 1 to x equals negative 1. So that's the radius convergence. So remember that that's the radius convergence, that this power series converges on the interval negative 1 to 1. Okay, so that's our green line and our blue line. Now, if I start out and I take out 1 plus x, there's 1 plus x. All right? Doesn't look a heck of a lot like 1 over 1 minus x. But now let's look at 1 plus x squared. So now what you can kind of see here is, yeah, well, down here, right, we end up having the curve move away from our curve of 1 times 1 over 1 minus x, but you'll notice that the parabola does actually start to actually approximate better 1 over 1 minus x. Now we'll go to 1 plus x squared plus x cubed. So this is the third sum, or the third partial sum, and you can kind of see, oh, it's gotten a better representation, right? So our initial red and then our second red, okay, they look more alike. I'm going to turn off the other two. Okay, so it's getting better. Now let's go to the fourth partial sum. Oh, that one looks even better, although we still have, like at the fourth partial sum, we're going to start to move back up towards infinity, so that's still a little off. But now let's look at this one. This is the ninth partial sum. So at the ninth partial sum, what you can see is look at how close, especially as we pass 0, right? Okay, so I'll turn off that third partial sum. Especially as we pass 0, what we get is we get a representation that's awfully close, okay, to our 1 over 1 minus x. Let's take let's take the 15th partial sum, 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th plus x to the 6th plus x to the 7th plus x to the 8th plus x to the 9th plus x to the 10th plus x to the 11th plus x to the 12th. And then we'll go to another one plus x to the 13th. That way we can kind of get that curvature that goes downward. Okay? And you could see, maybe even get plus x to the 14th. Okay? And look how close those are to approximating our 1 over 1 minus x along that radius convergence. Plus x to the 16th. Well, that's x to the 154th. That. Right? And you can see that as I get closer, as I increase the partial sum, what I'm getting is I'm getting closer and closer and closer to that curve, 1 over 1 minus x. And you can imagine that as I increase this number to infinity, as I increase the partial sum to infinity, what I'm going to actually get is 1 over 1 minus x. And so that's what we're talking about when we talk about approximating the function 1 over 1 minus x using the power series. Because that's exactly what's happening. We're getting closer and closer and closer to actually getting the actual function. So the cool thing about this is that this is actually going to allow us to do a lot of really neat stuff when it comes to writing our functions as power series. So like, let's say for example, I've got this. Okay, so take an example. And that's 1 f of x equals 1 over 1 plus x squared. Okay, now what I'm going to notice is I've got to note that I have a power series for 1 over 1 minus x, okay? Right? And you remember that that's the sum of x to the n. So if I rewrite this, this is going to end up equaling 1 over 1 minus a negative x squared, okay? And so if you can kind of take a look that the power series, or excuse me, that we can actually construct this particular function to look a lot like the one that we have a power series for. And then this is going to end up equaling the sum, n equals 0 up to infinity, and then we're going to replace, it's going to be negative x squared to the n, which is going to end up equaling the sum, n equals 0 up to infinity, of negative 1 times x to the 2n. Negative 1 to the n times x to the 2n. Excuse me. And there you go. So we've got an alternating series, right, times x squared to the n, the 2n. Okay? And now, if we wanted to, we could go in, we could run our ratio test, find its radius of convergence, and tell us an awful lot about what's going to happen with our series. Briefly, what we can see is that since we've got negative x squared to the n, right, when the absolute value of negative x squared is less than 1, then the series will converge. And the reason why we know that is because what we have here is we again have basically that geometric series. We have the geometric series, and so we just need that that's the case. Okay? So when is that the case? All right? So for x, right, greater than negative 1 and less than 1. And that's our interval of convergence. Let's take a look at another example. What if f of x equals 1 over x plus 2? Now again, I want to get into the form of 1 over 1 minus x because I know what to write there. And what I'm going to notice is that I'm going to actually notice that I don't have, I need to kind of switch this around a little bit. So this is going to end up being 1 over, and let's make it 2 plus x. Okay? And then what I'm going to do is I'm going to factor out a 1/2. Okay? So this is going to end up being 1/2 times 1 over 1 plus x over 2. All right? And now I'm pretty close to getting this thing right here. Okay? Now, one of the things that I'm going to note is I'm going to note that this is just going to end up being 1/2 times whatever the power series is that I'm going to generate, or that geometric power series. So this thing here is going to end up equaling 1/2 times 1 over 1 minus a negative x over 2. Okay? And then this is now going to equal 1/2 times the sum n equals 0 up to infinity of negative x over 2 to the n. This will then just be, what we'll do is we'll move that 1/2 in. So this is going to end up giving me the sum n equals 0 up to infinity of 1/2 times negative x over 2 to the n, okay, which is going to equal negative 1, or the sum, n equals 0 up to infinity of negative 1 to the n times x to the n over 2 to the n plus 1. And then what we can do here is we can find our interval of convergence, okay? Our interval of convergence will be, right, when x over 2 is less than 1, okay? And that's because if you look right here, there's the x over 2, and if you remember our geometric series, we need to make sure that that value, if that value is less than 1, that's like our x value, or r value. If x over 2 is less than 1, and that means that x will have to be greater than negative 2 and less than 2. And that's our interval of convergence, which means our radius of convergence is obviously 2. Okay, so just to kind of review as to what's going on here, what we've done, or what I've done is I've gone in and I've said, okay, so I'm going to start out with this function, and I want to get it into this form of 1 over 1 minus x. So what I need to do is I need to get this first value, that actually needs to be turned into a 1. And how I do that is by division, basically. So I've got 1/2, okay, so I'll pull out the 1/2, and then this will then be 1 plus x over 2. Well, I know how to change that into the negative. That'll be minus minus, all right? And so then that allows me to change this directly into my power series, my negative x over 2 to the n, okay? Brought in my 1/2, right, and then transformed it all into my summation. And then when I'm looking at my interval of convergence, because what I'm essentially looking at is a geometric series, I'm going to say, oh, okay, well, this term, negative x over 2, has to be less than 1 in order for this to converge. And there we go. So now we can actually start to look at some more difficult power series. But all we really want to do is, again, think about it in terms of that kind of fundamental relationship. So now let's say, for example, I've got f of x equals, and we've got x squared over x plus 2. And what I'm going to do is I'm going to rewrite this as x squared times 1 over x plus 2, or 1 over 2 plus x. Now, I already know what 1 over 2 plus x is because I just did that one in the last one. So this is going to end up equaling x squared times the sum, negative 1 to the n, x to the n, over 2 to the n plus 1. So we've already seen that before. Now, the cool thing here is that I can actually, since there's no n, right? Notice that there's no n in x squared, so I can just bring that x squared in. It just ends up being an additional x squared. So this now is the sum, negative 1 to the n of x to the n plus 2, okay? Divided by 2 to the n plus 1. And that ends up being my entire function, okay? So what you notice is that, you know, I basically just, I needed this thing here. This is a polynomial, okay? X squared. And this can be represented by a power series. So I'm just going to take the two of them. I'm going to multiply the two of them together, okay? And then, or actually I'm going to divide the two of them apart, represent the one as a power series, okay? And then take the other one as its multiplication, and then combine the two of them again at the end. Now the neat thing that we got going on here too is the interval of convergence here will be negative 2 to 2. Okay? Will be negative 2 to 2 because, just like in the last one, because the x squared term is finite. Right? it's not like you're adding on some to the nth power. All right, so we've got some finite power here, the x squared term, and you know, whatever x squared value you're going to get, you're just going to square that value, that finite term value, times a convergent sequence, and so consequently it'll give you a convergent sequence. So one of the key things that we want to get here is that if I multiply some kind of polynomial, right, by our power series, okay, then what we do is our interval of convergence is maintained. It's the same as what it was for the original power series. Okay, let's look at something that's maybe a little bit more complicated. Let's say, for example, that I have f of x equals 1 over x minus 1 times x minus 3. And I'll notice that that doesn't exactly look like something that I've used before or that I worked with before, but that's okay. What I'm going to do with this is I'm actually going to see that I can break this up into two representations that kind of look like I could turn them into power series. Specifically, I'm going to rewrite this as a over x minus 1 plus b over x minus 3. I'm going to use partial fractions. So using partial fractions, I'm going to get that a times x minus 3 plus b times x minus 1 is going to equal 1. Okay? I will let x equal 3. Okay? And when x equals 3, I get that b, so I'm going to get b times 3 minus 1 is going to equal 1. So that gives me 2b equals 1, and that b is going to equal 1/2. And then I'm going to let x equal 1, and so that's going to end up giving me that a times negative 2 is going to equal 1, so a is going to equal negative 1/2. So what that's going to do then is going to rewrite my partial fraction as 1/2 divided by x minus 1 plus negative 1/2 divided by x minus 3. Okay? And so that's going to then be, what I'm going to notice is that I can then kind of turn this into 1/2, or excuse me, a is negative 1/2, b is 1/2. That give me negative 1/2, and then I'm going to multiply that by negative 1 to give me 1 over 1 minus x. Okay? Plus, and then I'm going to take 1/2, I'll multiply it by negative 1, and then I'm going to also multiply it by 1 over 3, okay, to change that 3 into a 1. And that's going to then give me 1 over 1 minus x over 3. So now, this and this give me a power series. I have a power series representation for both of them. So this is going to then give me 1/2 times the sum n equals 0 up to infinity of x to the n. That's this first power series representation. Minus 1/6 times the sum x over 3 to the n. I bring in some of my values. I'm going to now end up being the sum n equals 0 up to infinity. And I can actually, because these are summations, I can combine the summations. So this is going to give me 1/2 x to the n minus 1/6 x to the n over 3 to the n. And something I'm going to notice here is that 6 equals 3 times 2. Okay, so this is going to then be the sum n equals 0 up to infinity 1 over 2 x to the n minus 1 over 2 x to the n divided by 3 times 3 to the n. Okay, so we continue to multiply. And this is then going to be 1/2, or the sum, n equals 0 up to infinity 1/2 x to the n minus 1/2 x to the n divided by 3 to the n plus 1. Now I'm going to pull out my x to the n. So this is going to then be the sum n equals 0 up to infinity of 1/2, okay, times 1 minus 1 over 3 to the n plus 1, okay, times x to the n. And that, ladies and gentlemen, is my power series representation. Okay? So if we can somehow transform whatever we're working with into some form of 1 over 1 minus x, all right, which is some practice, then what we'll end up getting is a really great power series representation. Okay? This ends the lesson.